In this lecture, we'll talk about the Chinese Remainder Theorem, which is the focus of section 7.6 of Dummit and Foote. And in this lecture, and in all of section 7.6, all rings that we talk about are required to be commutative rings with identity 1 not equal to 0. And in this first video, what I want to do is just set up what does the Chinese Remainder Theorem say in a simple, relatively simple case, and then we'll move on to the general case. And in order to do that, the first thing that we need to talk about is direct products of rings. And this should feel really familiar because it's going to be very, very similar to the setup of our discussion of direct products of groups. So if you have two rings, R1 and R2, and remember, these rings are commutative rings with identity 1 not equal to 0. The underlying set of the ring R1 cross R2 is ordered pairs R1, R2, where R1 is in the first ring and R2 is in the second ring. What are the operations? The operations are defined component-wise. In a direct product of groups, the operation on the direct product was defined component-wise. Here we have two operations, an addition operation and a multiplication operation, and they're each defined component-wise. So R1, R2 plus S1, S2 is R1 plus S1, R2 plus S2. R1, R2 times S1, S2 is R1 times S1, that's multiplication in R1, R2 times S2, that's multiplication in R2. Okay, this is a ring. Checking this, well, along the way to checking this, it's like checking the direct product of two groups is a group, but you also have to check that this behaves nicely with the multiplication operation. You have to check things like that multiplication is associative and the distributive laws hold. And each piece of this is very straightforward using the fact that R1 and R2 are rings. And you really should check this. You should write down the details one time to convince yourself that you know how to check that this is true. Okay, so the next thing that I want to talk about is homomorphisms from a ring to a direct product of rings. And the idea is that you can check if a function is a homomorphism by looking at what it does inside of each component. So making that more precise, we have this function that goes from R to R1 cross R2. And there are these two projection homomorphisms from R1 cross R2. The first one, the projection pi1, goes to the first factor R1. And the second one, the projection pi2, goes to the second factor R2. Just takes the pair A comma B to A in the first case and to B in the second case. So, okay, we can compose these functions and take something in R, send it to R1 cross R2, and then see what is its first component and see what is its second component. So composing gives functions pi1 following phi, which goes from R to R1, and pi2 following phi, which goes from R to R2. And you should check that the things that need to be true for phi to be a homomorphism into this direct product are exactly the same conditions as separately requiring that both of these two compositions are also ring homomorphisms. So the statement is you should check that phi is a ring homomorphism if and only if both pi1 following phi is a ring homomorphism and pi2 following phi is a ring homomorphism. And that is straightforward, but you really should check that it's true. Okay, so I'll note that all of this is for the direct product of two rings, but you can generalize this in the obvious way to a direct product of many rings. So just like we talked about the direct product of two groups and then the direct product of many groups, you can do the same thing here with rings. So I'll pause and erase, and then I'll talk about the particular example of some direct products involving Z mod NZ for different n. Let's think back to our discussion of Z mod MZ and Z mod NZ. We've already seen that if the GCD of M and N is 1, then Z mod MNZ is isomorphic to Z mod MZ cross Z mod NZ. And we proved this earlier for groups. But in fact, something better is true. Not only is there an isomorphism between the groups Z mod MNZ and the group Z mod MZ cross Z mod NZ, but there is a ring isomorphism between them. Okay, so we'll see this in a minute. Let's also recall one more thing. We saw the sum of two ideals. Remember, the sum of I and j is just the collection of all of the things that are something in I plus something in j. So if you take mz plus nz, what do you get? Well, every ideal in z is principal. It's generated by something. It's generated by the GCD of m and n. So it's this principal ideal generated by GCD m n z. Okay, so the GCD being equal to 1 is equivalent to mz plus nz being the whole ring Z. So that is a special property that gets a definition. Let's say that A and B are ideals in a commutative ring with identity 1 not equal to 0, R. Those ideals are called comaximal if A plus B is equal to the whole ring R. Okay, so comaximal is not directly related to being maximal. Comaximal is a property that you attach to a pair of ideals. All right, so now let's state, what does the Chinese remainder theorem say for k equals 2? In the next video, we'll see what happens for the general case where you have more than 2 ideals. All right, so let's take A and B to be ideals in R. We can take this map that goes from R to the direct product R mod A cross R mod B, defined by taking element little r to R mod A, R mod B. Well, what is that? R mod A is an element of the quotient ring R mod the ideal A. So what are the elements here? They're left cosets of A. So that is the coset R plus A. And similarly, R mod B is the coset R plus B. You can think about this either way. Both notations are good to be comfortable with. So this map is a ring homomorphism. And the kernel of this ring homomorphism is A intersect B. So if A and B are comaximal, we'll show that phi is surjective. And this intersection of these two ideals is the product of these two ideals. Now, applying the first isomorphism theorem for rings, we'll show that R mod the kernel, this product, A times B, well, that's the same thing as R mod the intersection of A and B, is isomorphic to the image. And since this is surjective, this is R mod A cross R mod B, and this is an isomorphism of rings. Okay, so let me just say first, recall, the sum of two ideals, I and J, is just all the thing, it's everything of the form something in I plus something in J. The product is a little more complicated. Remember, the product of two ideals, A times B, is the ideal generated by all finite sums of elements of the form little a times little b, something in A times something in B. So we need an ideal to be closed under addition. And if you just take products of elements in A and elements in B, that set isn't necessarily closed under addition. So you have to take all finite sums of these things. So it's good to remind ourselves of that. Okay, what does the Chinese remainder theorem say for the case where R is equal to Z and A is MZ and B is NZ? Well, in the case that A and B are comaximal, MZ and NZ are comaximal, that is when the GCD of M and N is 1, that's saying that this map is surjective and the intersection is equal to the product. And it's exactly telling us in this case that Z mod MNZ is isomorphic to Z mod MZ cross Z mod NZ as rings. So in the next video, we'll prove the Chinese remainder theorem for k equals 2. Then we'll state what happens for general k, and we'll give a proof that is going to follow pretty directly from the k equals 2 case plus induction. And then we'll see an application at the end of this lecture.